Hello, welcome to ME154. This is the last series of for the lectures before we end the lecture part of this course. So our last topic of this semester will be bearings. Now, okay, so I believe some of you have an idea of what bearings are. But this time we'll be focusing more on how do I pick bearings given a product catalog? Let's say you're a in the procurement division and you are given a series of specs for the bearings that your fellow engineers will need. And at the same time, you are browsing product catalogs from different bearing manufacturers. So what we want to look at today is first, how do we relate the requirements of the bearings to the properties of the bearings that we truly need. And then for the third part, we're going to just explain what reliability means in engineering. So I know in English we have at least some different levels of word usage. So for example, if you say reliable, there is the vernacular, the common definition for reliable, and then we have an engineering or a jargon level definition. So we are going to jargonize reliability in this lecture. But first and foremost, let's establish what are bearings. Like, why do we use bearings in the first place? Okay, for those who don't know what bearings look like, this is one kind of bearing. So as you can see here, this bearing has been cut open uh, at, at the half point. So half of it is still sealed as usual, and then half of it is kind of exposed for you to see what's inside. So the purpose of the bearing is first and foremost, it's meant to connect rotating elements, or at least things that fully rotate or things that just oscillate, to a fixed support. So this is important. The bearings are meant to connect rotating elements to some fixed support or a rotating support. So they likewise they do bear loads. They are expected to carry loads from shafts, from gears, from pulleys, etc. All right. So what is the other purpose? So when it comes to friction, there you should know about the three kinds of friction coefficients. So there is coefficient of friction for static forces. There is a kinetic coefficient of friction, and then there is the rolling coefficient of friction. So which one of those is the lesser one? Of course, it's the rolling friction. The purpose of bearings is to reduce the amount of friction that is being experienced by the part so that your system will live a little longer. So you can either do this by putting rolling elements, such as here, what you see in this animation, or you can put in a viscous liquid like lubricant or oil and whatnot, and that will help you reduce the wear and tear on your shafts, on your components, and thus let it live a little longer. So what are the types of bearings? I'm just going to simplify. There's way more than what I'm going to show you right now. But in general, you'll encounter at least three categories. The first is the journal bearing or the plain bearing. So this is just two cylinders that are filled with liquid inside. So it can be any kind of lubricating fluid. That one is under tribology. I won't be able to answer what kind of properties that you need there. What you just need to know is that journal bearings are usually just filled with oil. It can be filled to the brim or just filled to a particular level. The second one, which will be the focus of our two lectures, is the rolling contact bearings. So instead of using oil, you use rolling elements, where that's balls, pins, and whatnot. As long as they roll, you can use them for rolling contact bearings. For the third, this one is of a different loading type. These are thrust bearings. So as the name implies, thrust bearings are meant to carry thrust or actual forces along the shaft. So thrust bearings are used in particular sets of applications if you're expecting the shaft to be pressed against a support or something else. You might want to use thrust bearings. So just like what I mentioned before, we're going to be focusing on rolling contact bearings uh, here. So what's inside? What are the parts of a rolling contact bearing? So let's examine. So this is a full bearing that's also sectioned, so you can see inside but only partially. And this is the exploded view. And what you see in the exploded view is that, of course, there is sealing to keep your elements in place. Um, More obviously, you have two sets of metal cylinders. You have an outer ring and an inner ring. Another name for these components are races. So when you say inner race, it's the smaller of these rings. When you say outer race, it's the bigger of these rings. Now, inside the races, that's where you will find your rolling elements, whether it's balls or pins or some other kind of roller. You'll find them in between these rings. And normally, they're kept in place by either cages or the seals themselves. Now, when it comes to rolling elements, um, in this example at least, they are indeed caged. So as you can see here, the rolling elements here are caged up so that they don't move around in the direction that they are not supposed to. So that kind of helps. Not all bearings will have cages in some of them. And here are a few of the many configurations that you might see. Oh, okay. So do we have to know all of these? At this stage in your undergraduate career, not quite yet. Just know that there are two general types of rolling contact bearings. There are the ball bearings, so ball bearing bearings, and then there are the roller bearings here. So I believe the difference is quite obvious, but perhaps you might be interested. Okay, so what's the actual difference? Aside from the optics of these two, do they perform differently? So the answer is yes. They do perform differently. So let's start with the ball bearing. The ball bearing is actually one of the easier bearings to assemble, because it's essentially just two races, a set of spheres, and then you just cage them if you want to. Now with the ball bearings, you have very minimal surface contact. So these bearings can last quite a bit. However, they can't bear as much load compared to the roller bearings. Another difference between the ball and the roller bearings is that these spheres the shape itself allows them to carry some actual load. So when you buy ball bearings, you can expect some actual resistance, at least some, even if what you bought was not outright mentioned to be able to carry actual load. They'll be able to carry at least some of it. Now, when it comes to rollers, rollers try to have extremes on those descriptions for the ball bearings. So as you can see with the rollers, you have more surface area contact. So you have more surface to spread out any radial load that the bearing is experiencing. So these bearings can take much more load compared to the ball bearings. However, if you're expecting any axial or thrust loads, you might want to angle your rollers. Like for example here, you might want to angle them so that they can also bear axial loads. Another thing that you have to notice that for roller bearings, they are at least harder to assemble. they require more precise alignment compared to ball bearings. And as such, usually you'd see ball bearings in the more consumer grade types of bearings. So yeah, ball bearings, they're kind of a bit more rounded overall compared to the rollers. And for the rollers, you kind of expect higher load bearing capacity in exchange for some drawbacks. All right, so those are the difference between the balls and rollers when it comes to loading. Now let's talk about the loading itself when it comes to bearings. Because one of your races is rotating, even though you have, perhaps you may only have a static kind of loading, that race will experience dynamic loading. So for example, in this journal bearing, um, the real look inside a journal bearing that's filled with oil is that sometimes there will be sections of the journal bearing that will have a lot of oil, and then there will be a section that has really, really too thin of an amount of oil, perhaps too thin for comfort. And this kind of region here is going to change with respect to time. So the distribution of oil, most of the oil will not stay here forever. This place will not be oil thin forever. And that is part of the complication when it comes to accounting for the loads on bearings. So if this is for a bearing that is filled with oil, how about rolling contact bearings? If you look at rolling contact bearings, this is just an animation of what kinds of loads the two races, the inner and the outer, are experiencing. As you can see here, it's really dynamic, and there might not be a consistency in the magnitude and the direction. So the thing that you have to note here is that if one of the races is rotating, for example, if the inner race is rotating, the inner race, from the inner race perspective, this load is traveling around it. And when it travels, it's not quite a point load, it's going to be a distributed kind of load. So this is a type of dynamic loading that is very hard to characterize from the analytical perspective, at least from where we are now at this point in our undergraduate program. So we will have to climb some hoops, or we're gonna go through some hoops in order to help understand the lifetime or the life cycle of a bearing. Now, when it comes to loading, again, we have two potential loads. We can have loading from the sides. So this is radial loading, F sub R. Or we can have loading along the shaft, which is the thrust or the actual load, F sub 8. All right. So if these are the loads, what does a bearing running out of life look like? So when a bearing starts to reach its operational lifespan, its design lifespan, it will start to have little pock marks. We call these spalling in the bearing subfield. So you can have these little potholes, kind of like substandard concrete roads that we see all the time. So if you leave the bearing for too long, it will develop these pock marks, and these pock marks are actually signs of fatigue. So this is just an example of a spall that keeps growing over time, and it's not addressed. So when your bearing develops a lot of these pock marks or spalls, they might not last long. They could get destroyed during operation. Hence, we have to keep track of how long the bearing has been there, and we have to know when to replace it so that we don't get any unfortunate accidents. So I've already mentioned it now. We are not going to use strength of the material in order to determine the limits of the bearing itself. So this is one of the differences between bearings and the elements. Even though in the past we may have used strength in order to determine where the bearings kind of have to be replaced, nowadays it's more acceptable to just count the life cycle of the bearing and then work our way around that in order to determine what kind of bearing that we should buy from our manufacturer. So at this point, instead of strength, we look at the lifespan of the bearing. So the lifespan of the bearing can have two quantities. So the first quantity is the revolution count. This is just the cycle count or the number of revs that the bearing has undergone in its entire lifetime. And in Budinas and Nisbet, it is denoted by this sans serif capital L. So when you see straight laced L, it's just the count of the revolutions that the bearing has undergone. The second quantity is the operational time. Now, this is where it gets a little confusing. So, even though this is the last item, please keep in mind the difference between the variables used. So, when you see a very fancy curvy L, it usually denotes operational time, which is normally in hours. It can be given in minutes, but you have to convert them into hours. There's a reason why later. So, again, there are two possible quantities. You can just count the number of cycles or you can count the number of hours that the bearing has been active. So, okay, what do we do next? So, this kind of bearing life, this concept of, okay, so how long will the bearing last, has been codified by the American Bearing Manufacturers Association, or ABMA. According to ABMA, they want bearings to be rated to a particular number of cycles. And this number of cycles is known as the rated life, or curvy L sub 10. Curvy L sub 10. What is the benefit or what is the definition of rated life? So, rated life of a bearing, a particular model of bearing, is the number of hours that bearings in one set can exceed, and not just exceed, 90% of those bearings have to exceed. So again, the rated life is the number of hours that 90% of a single batch of bearings can exceed. So, like for example, if you make just one model of a bearing, so let's call it model one. So your model one bearing is designed with a rated life of, let's say, 1 million cycles. So when you rate your model for 1 million cycles, you expect that 9 out of 10 of those bearings will come out okay, even if they exceed 1 million counts cycles. So with the thing with rated life is that you can also see with the subscript, this is L sub 10, but the number of bearings that exceed this number of hours is 90%. So you kind of have to work around this swapping. So when we say L10, it's 90% of a component surviving. If it's L80, it's 20% of the component surviving. You don't really want L80 to be your basis. So this graph is one example. So there should be not a lot of bearings um, failing at this dashed line. So why do bearings fail in percentages? So that's the thing with fatigue. Fatigue is a very statistical phenomenon. Sometimes you can't really account for manufacturing defects or casting defects and whatnot, and those can play a part in the eventual demise of one unit of your bearing. But because there is some unpredictability with the manufacturing of the bearings, some of them will survive, some of them will not survive. The important thing is that a lot of them, especially 9 out of 10 of them, will survive the rated life. So this rated life is normally 10 to the 6 revolutions or 1 million cycles. Now, okay, so this is rated life. When we think of rated life, of course, it's not the life of the bearing with nothing loaded onto it. So, of course, this rated life is paired with a load property. And that load property is something that we call the catalog rating or the C10. The C10 is the radial load. So, it's the load from the side that corresponds to the rated life. So, okay, if your Model 1 is designed to survive 1 million cycles and it is rated at 4 kilonewtons, then that means if you load 1 unit of the bearing for 4 kilonewtons, which is the catalog rating, 9 out of 10 chances it will survive beyond 1 million cycles. So again, if your catalog rating for Model 1 is 4 kilonewtons, 9 out of 10 chances or 9 times out of 10 that bearing will survive 1 million cycles of being loaded 4 kilonewtons. 9 out of 10. So these two come in pairs. So these come in pairs. So the catalog rating corresponds to rated life. The rated life corresponds to the catalog. Now, if you plot out, okay, so this is just one point uh, on the load life relationship. Now, if you try to test out, okay, so if you're a manufacturer, let's try out different ratings, different loads, and let's see how long the bearing lasts. So if you do multiple tests, as in hundreds of mod units subjected to different loadings, you'll develop this kind of relationship. In general, bearings tend to follow this kind of behavior. So this plot here is a log curve. So I have a log relationship between the load, letter F here, and the life, which is letter L. The relationship comes out like this. So it's a log curve. If you unlogarithm it, you will get this kind of relationship between the force and the life. So what you end up with is here is a constant term, which is the radial load F here times the life L raised to 1 over A. Okay, what is that 1 over A? It's kind of a constant denoting the type of rolling contact element. So if you have a ball bearing, your A here is 3. If you have a roller here, it's 3.33. And the neat thing here is that this relationship is true at every point of your load life relationship. So you can compare 2 points. You can compare the rated condition. So the rated condition here, which has the catalog rating corresponding to the rated life. And then you can compare that to your design point, the application of the bearing. So, okay, you see the rated point on your brochure, but you intend to use the bearing for another kind of loading. So, this is the design point. In order to solve for design-related quantities, you just equate the form, this term, which is in the rating point, to the design point, as shown here. So this is a constant relationship. If you substitute the rated parameters and the design parameters, you will end up with something like this. Okay, so what are these? So on the left-hand side, you have your rated terms. These are the properties that you will see in the catalog. Now, for example, you have C10, this is the force, this is the load, and then you have curve VL, which is number of R's, and N sub R, which is the rated speed times 60. Now, where did 60 come from? Normally, this rotational speed and sub R is given in RPM. So it's in revs per minute. And what you want to do is, in order to turn this entire bracket into just revolution count, such as here, this sans serif L, you have to multiply RPM by 60 in order to turn it into RPM per hour. So you multiply hours with RPM per hour, you get revolutions. So this thing in the parentheses is the same as the sans serif L. Don't worry about it. And on the right hand side, you have your design parameters. You have your design load and you have your design operational time. Now, if you're solving for design properties, you have two routes. So it's possible that you already have a loading in mind and you just want to find out, okay, how long will my bearing last if I pick this kind of bearing? It can also be the reversed, I mean. You know how long you want your bearing to last, so how much load can you apply to the bearing given that you're buying a particular bearing model that has this catalog rating and this long of a rated life. So here is just an illustration, just to differentiate the ball bearing from the rollers. So like as you can see here, the ball bearings have a little less load carrying capacity compared to the rollers. However, the ball bearings, they are easier to assemble and they can take some actual loading in comparison to the roller bearings. Now let's go to some examples. So this is an example from Budinas and Nisbet, 9th edition. It's a little modified. So as you can see here, you are a procurement officer and you need roller bearings. Your roller bearings, as per your technical team, is supposed to operate with 400-pound force of radial load. 400-pound force of radial load, and it's supposed to run at 1800 RPM for 6,000 hours. So after 6,000 hours, it'll be replaced with a same model, different unit, and so on and so forth. Now, for 90% reliability, SKF, so SKF is a bearing manufacturing company. It rates all of their bearings at 1 million cycles of life. Given this, what catalog rating in kilonewtons should you look for? So again, you have your design parameters and you are shopping for bearings. Now, the manufacturer rates all of their bearings to 1 million cycles or 1 million revs. Given that, what catalog rating, what C10 should you be looking for? So let's break it down. Let's look at our given first. You have two given, you have two categories for the given. The first is the one that comes from the manufacturer, which is your L sub 10. This is 10 to the 6 cycles, nothing new. And then these are your design properties. Now, okay, how do you find the catalog rating then? So we just apply the equation that we saw before, which is the radial load times the rated life, or rather the life of the bearing, raised to 1 over 8. So you have this quantity here, this quantity, and we're just going to rearrange in order to find what is C10. Whoa, what is this? So this is letter A of our equation. So since we're looking for roller bearings, our A here is 3.33 or 10 over 3. All right, you might want to ask, okay, so this is the rated side of your equation. This is your design side of the equation. Do we have a rated hours? Do we have rated speed? No, we do not. However, this entire quantity here in the parentheses is actually equal to sans serif L, or the rated life. So you just substitute this term, substitute this with 1 million cycles. Yeah. You turn this entire parenthesis into just sans serif capital L then. So this is legal. And now all you have to do is to rearrange the equation. You isolate C10 and you move L10 here to the other side. And you'll get this kind of expression. And from this point on, you just substitute all of your terms. If you look here, all of the units are correct. It's in pound. This is in pound force. This is in hours. This is in RPM. So the 60 term here is just right. And if you plug these all, you'll get this quantity. 2,789.6 pound force. But again, you're looking for kilonewtons, not pound force. So the conversion factor is as follows. 1 pound force is 4.45 newtons. And doing so, you get 12.41 kilonewtons for C10. Is it this easy? Yes, it's this easy. At least in this point. All right. So just to get the ball rolling, okay? So if let's say we have ball bearings instead, like you're shopping for ball bearings instead, will your C10 be higher or lower? So that's a good question. Okay, so now we continue. So all right. So the load life situation is quite easy. So most of this just revolves around this kind of equation. Now we're going to examine uh, the thing that you see in this description. So so far we've assumed that all of this is around this particular value, which is 90% reliability. Now, what if we want to select for bearings that have a much higher success rate for a particular rated life, or rather, um, a higher amount of success when it comes to 1 million cycles? So, before we do that, we have to examine the quantity known as reliability. Now, reliability just tells you the chance of your bearing to survive a particular amount of operational load. And this load, when you plot them out, like for example, if you do hundreds and hundreds of tests on bearings of the same model but different units, you will see that the distribution of the failure rates, or rather the um, load and the operation are at which it failed, will follow this thing called the Weibull distribution. I'm actually not sure if it's Weibull or Weibull. Um, you can consult the internet for the proper pronunciation. I know I remember the proper pronunciation, but I've kind of forgot already. So, what is the Weibull distribution? Let's just call it Weibull. Let's pretend that it's actually Weibull. Yeah. So it's a viable distribution. Um, a viable distribution is kind of special because in statistics we kind of get used to the normal distribution wherein we get the centralized bulge and then you have distributions left and right. Now the viable distribution can take into account skewness in the graph. So you can have your bulge, the bulk of your data to the right, maybe to the left, and whatnot. The Weibull makes it essentially possible. So what does the Weibull distribution look like? I keep defaulting to Weibull. I'm sorry. So okay, so I'm just gonna pronounce it as Weibull at this point. I'm not sure what is the proper one. Okay, so what does the Weibull distribution look like? It can look like any of these. So there are actually two forms of the Weibull distribution. There's the probability density function, and then there's the cumulative density function, or the CDF. We're actually going to be looking at CDF instead of the PDF. You might be more familiar with the latter, instead of this one, from one of your courses, perhaps AMPE 134. I think AMPE 134 looks at the probability density function. For this case, we look at the cumulative density function, which kind of just describes, okay, so what's the chance that this dependent variable x will have a value of so and so or less. So essentially, you're just accumulating the tolerance of a particular quantity. So as you move to the right, there will be more. The value will just keep rising until it becomes 100%. That is a cumulative density function. There is no dip after this, it just accumulates. All right, so this is a little confusing. What else do we have to go by? So okay, so this is the Weibull distribution. This is a cumulative density function. What then is the form or the function that we're working with? And the function is this. So f sub x. So f sub x here is the Weibull distribution. This is not reliability yet. It is defined as a piecewise function. So if your x is less than 0, it is 0. So it doesn't exist beyond this point. However, if your x is equal to greater than 0, then you get this function here, which is an exponential function with a lot of special variables. So x here is the one that's in the x-axis here, but what are these? What are these two new properties here? So this is the interesting with the Weibull distribution. These two parameters here control the skewness, or at least part of it. So the first one is k in this expression. It can be a or b. This is the confusing part. Just know that this k is the exponent, all right? So this is the exponent in the function. This is what we call the shape factor. The shape factor kind of dictates the form of your distribution. So it can be this kind of L-shaped conglomerate here, or it can be an S shape here. So the shape factor controls that. And then you have the scale factor or the denominator inside this exponential function. So this denominator, the scale factor, it kind of describes, okay, so how spread out is this cumulative density function? Is it all tight here like this, or is it kind of spread out like this one? So to illustrate, here are some Weibull distributions with altered factors. So if we alter only the shape factor, we get this. So as you can see here, as we increase our shape factor alpha, the graph goes from sideways L to a more S-shaped kind of curve. It kind of looks like the um, phase, the steady state phase angle of a harmonically excited vibrational system, but maybe you've already forgotten that. So the shape factor, the exponent of the exponent controls the shape of the distribution. Now, the scale factor controls the amount of distribution, like how spread out is your data. So if your shape factor, your beta in this case, is kind of very small, your entire function will add up to 1 immediately, like very close to the x equals 0. But if you have a very high scale factor, then that will be a much more distributed function. It will accumulate to 100% at um, a much farther distance. Right. So when x is life or dimensionless life, okay, so now we're going to contextualize this into reliability. So x here is going to be re- our life or dimensionless life, whatever that may be. We won't define it just yet. While f of x, which is our y-axis here, is going to be the chances of failure. So this curve, this y-axis is the chance of failure. This is the life of your bearing. Then we can define reliability as the sort of, so I'm gonna look for it here. Okay, so it's not here. So we're just going to assume, okay, so right now what we're seeing is x is dimensionless life, and this y-axis here is the chance of failure. So as you increase, as the bearing continues to survive, or rather, as you increase the life of your distribution, there's higher and higher chances the bearing may fail. So that's what the increasing graph represents. So as you go further, as you expect more life out of your bearings, more and more of them will have a higher chance of failure. Now, there is something to be said with the scale factor itself. The scale factor and the shape factor in particular are experimentally determined. So these are not things that we can assume to be constant um, for every set of bearings. So these have to be given. It's either supplied by the manufacturer or it's given to us by the problem maker. So the problem maker or the examiner. When it comes to the scale factor, if you see here, your beta equals 0.5 is really tight. So this signifies that um, a lot of your units are failing quickly, like probably much earlier than you expect. Now, if you go a little further, if you go to beta equals 4, you see that a lot less of your units are failing immediately. So there's something that we can say about beta. So if your beta is really low, like it's less than 1, it's probable that the cause of death for your units or your components are probably inherent in the design. So like you may have to go to the drawing board and go back to the drawing board and rework some part of your component in order to make it sturdier. Otherwise, it's just going to keep failing constantly, and you will lose the trust of your customers. If your scale factor after experimentally finding out that value is equal to 1, then it's perfectly random. Like it could be a defect in the manufacturing, or it could be just the bearing noped out, like it just died on its own terms. Now if your beta is greater than 1, this is the good one. That means your part is well engineered, and any kind of failure that it sees is because, well, it just ran its course, it just died of natural causes. So that could be extreme spalling, or it could just have broken, or it could have just exceeded its rated life. So the higher your beta is, or higher your scale factor is, the more sturdy your part is actually in real life. So now, all right. So those are two parameters of our Weibull distribution. We're going to add the third. Now, the third one dictates what is the starting point of your rise in your cumulative density function. So we call this the threshold value. This is denoted by mu in this expression. So this mu kind of controls where the rise of the Weibull distribution starts. So this is an example. So as you increase the mu here, the much the late the later the rise of the curve occurs. So again, if you increase your threshold factor, the function rises much later, and kind of denotes this threshold factor. It signifies the early sign of failure. No, I can't really say that yet. It's probably more related to reliability. Scratch that, scratch that. So, as from now, there are three parameters. There is the shape factor, there is the scale factor, and then this is the threshold factor. All right. What else do we need to know? We also need to know that something happens to this equation if x minus mu is equal to beta. So if x minus threshold over the scale factor is equal to 1, then you get this kind of special function. It becomes 0.632. This 0.632 is, it will come up later into the lecture. Okay, so what else do we know? All right. So far, these distributions indicate the chance of failure. Reliability is actually the opposite. Reliability indicates not the chance of failure, but the chance of survival. So if this curve is the chance of failure, then of course the reliability will look kind of the reverse. So instead of it increasing with increasing life, reliability should decrease with increasing life. So the function would look something like this. Reliability is just 1 minus the failure function or the Weibull distribution. And you just end up with this one single exponential function. You lose that 1 minus e raised to something. No, you lose the 1 minus here and just becomes this sole exponential function. Now, at this point, you might be wondering, okay, wait, why did we use this expression when Budinas and Nisbet uses others? This form is the more generic Weibull distribution form. Budinas and Nisbet use different variables for it. I'm not sure why, but I'm going to present them now. So this is what Budinas and Nisbet use. It's kind of confusing, but if you look at the functions, the scale factor is still the exponent of the exponent. The shape factor is still the exponent of the exponent. The scale factor here is a difference of two terms, but the threshold value is still the threshold value, which is x naught. X naught makes it easier to remember at least. That's right. B is the shape factor now. Sadly, our scale factor here turned into a difference of terms. That will be difficult to remember, but just keep that in mind. So, right. Now, let's define dimensionless life. Dimensionless life is now the actual life over L sub 10. L sub 10 is, of course, 1 million. So, x is equal to L over 1 million. It's that easy. That is x. Okay, so reliability now indicates the chance that your product or the unit will survive after a particular amount of life, which is number of cycles. So now we also have this threshold value. So what does the threshold value represent in reliability? This represents the one that failed the soonest. So you did multiple tests on multiple units, and this is the first one that gave way. So this is the sad one. This is X naught. Now the scale factor parameter here, we'll just define theta separately, but you don't actually need to separate theta from this set of terms. Now we just call this scale factor parameter. I'm not sure why where this arose, but yeah, we just call it the scale factor parameter. So when you subtract this to the threshold, it will result in a CDF value of 0.632. 0.632, that is amazing. 0.632 arose again. So yeah. Other than this, just take note that the scale factor is theta minus x naught. That's all that you need to know. And the graph would look something like this. So it's the reverse of the failure function. The failure function rises with increasing life. The reliability function decreases. Like there's less and less of your unit surviving after a particular point. And this is the graphs when you change the threshold value. So again, the threshold value is the first unit that failed. Like it, it's the absolute failure of the entire batch, and that's where everything goes downhill. All right, so that's reliability. So this is the actual reliability function. Just take note. This is how Shigley writes it, but the more generic term, the one that mathematicians and statisticians use, kind of resembles this a bit more. All right. So this is a distribution function. When it comes to distribution functions, of course, just like the normal distribution, we are interested in statistical parameters. What are these statistical parameters? That is the average or the mean, the median, and the standard deviation. The thing with the Weibull distribution is that we can't really use the normal definitions of mean, median, and standard deviation. That's because of the skewness of the graph. And in order to characterize those parameters, we need to borrow from a very special kind of function, which is the gamma function. The gamma function is really, really weird. It is a very special function that if you look at it, you might wonder why does it exist? Like, why should we care? The reason why we should care is that it's going to help us define some statistical parameters of the Weibull distribution. So even though it looks a little weird, we have to entertain its existence. Now, okay, so sir, do we have to use this integral? Do we have to plug this integral to my scientific calculator? Yeah, well, you can do that. However, we are going to use a table instead. So, just like in your high school, perhaps you've encountered the normal distribution with a set of tables for values. It's kind of like a steam table. We do have table A-34 in our ME154 cheat sheet. You can refer to that. Or you can approximate infinity here with a very large number. So like if you insist, okay, so I'm gonna use 100 on this last border of my integral function. I would just advise to use this. Just use A-34. All right. So okay. So after we use A-34, so what do we use this for? So now let's define what dimensionless life is as a function on its own. So far we've only looked at the reliability of the entire set of a batch, or rather reliability of a batch of units. Now, X dimensionless life itself can be defined as this. So this is the threshold factor plus your scale factor multiplied by this quantity. Oh, if you look at this, we just rearranged this reliability function into a different form. So this is the definition of dimensionless life. This is just the equation rearranged so that X is isolated. So what is the mean of this entire function? Well, glad you asked. The mean of this function is defined as this. So mean here is mu. So mu of the dimensionless life is equal to the threshold plus your scale factor multiplied by the gamma function of 1 plus 1 over the shape factor. So, right? So, 1 plus 1 over the shape factor. Next is, okay, what is the median? The median here is 50%. So, this is important. If we say 50%, that means, oh, we didn't look at the median. Okay, so I'm just gonna show you later what the median is. So this is the standard deviation. You have a square root of two gamma functions. You have this gamma function here, and then you have a gamma function that's squared. And then you have the coefficient of variation, or the root mean square, which is just the standard deviation divided by the mean of the distribution. Whoa, this is confusing. What you just have to know is, okay, I use this function to get to this statistical parameter. That's it. No more, no less. So can we have a trial? Yes, we can have a trial. So right now, okay, so we have a ball bearing model, and we, as the manufacturer, tested several hundreds, maybe thousands of these ball bearings of the same model, and we came up with the following statistical parameter. So we saw that it looks like a Weibull parameter with these factors studied. Now, with these in mind, so this came from the study itself. Find the number one, mean dimensionless life. Number two, the median dimensionless life. Number three, the 10th percentile value of dimensionless life. Okay, what is that? We'll discuss it later. And then the fourth and the fifth is just the rest of the statistical parameters. Okay, so where do we start? So the first thing that we need to do is when we look at our statistical parameters, oh, There's gamma here. There's another gamma here. We look for our gamma function results. So fortunately, we only need two gamma results here. So we need a gamma function result for 1 plus 1 over b, and we need a gamma function result for 1 plus 2 over b. So what you have to do is first go to the A-34 table, compute for this 1 plus 2 over b or 1 plus 1 over b, and then find the corresponding gamma function value. Now, what if you don't find the exact 1 plus 1 over b or 1 plus 2 over b? Then you know what to do. Of course, you interpolate. So the interpolation is a skill that you'll be using for a very, very long time, even after engineering, even after this course. So you might as well keep that skill sharp. So find the gamma functions. If you interpolate, you will get this particular value for 1 plus 1 over b. And for 1 plus 2 over b, you should get this value, 1.202. So, okay, now we've gotten the gamma function value. So what's next? We look for the mean now. So the mean has its own definition, which is mu equals threshold plus scale factor plus the gamma function of 1 plus 1 over b. And it is denoted by this function here. So these functions, we just plug them into this equation. Again, the shape, the scale, and the threshold values all come from experimental values of hundreds of thousands of units of the same model. So it's only after you do this that you can seek out, or you can try to seek out statistical parameters of your bearing units or bearing models. So just plug and play. You will get the mean of 4.03 dimensionless life. Okay, so what about the median? We don't have a particular expression for it. However, we do know something about the median. The median is the halfway point of the values, meaning that it's 50-50. If you're to the left of the median, quote unquote, is you have 50% of all the bearing units, and beyond that, there's 50% of all the units as well. So when we look at their generic x function, we can just substitute 0.5 for the reliability here. So why did we substitute 0.5 for r? Again, it's the median. 50% of the bearings survived this dimensionless life rating. That's what it's trying to say. So r is replaced by 0.5, and then the rest is plug and play as usual. So just plug the threshold, the scale, and the shape, and you get this 3.487. So you have a mean that's greater than the median. There are implications to that, but we will not talk about it right now. We still have things to solve. So next, we are being asked for the dimensionless life for the 10th percentile value. Okay, so 10% percentile value of dimensionless life. So, okay, so given this, okay, so the last thing that we looked for was 50-50. So 50% failed, 50% success. When we say 10 percentile value of dimensionless life, what does that mean? So what does that mean? Your R is at 90%. When we say 10 percentile value, it's 10% of your parts have failed. So your reliability should be at 90%. And this one is simple. You just substitute again to this generic equation. Instead of 0.5, we plug in 0.9. And if you plug in 0.9, you'll get 0.993 for the dimensionless life. Now, this dimensionless life is awfully close to 1. And that means the dimensionless life, L over L10, is essentially having L be equal to L over 10, L sub 10, which is correct. 10th percentile value of dimensionless life is actually the dimensionless rated life itself. All right. So for the rest, it's just plug and play. You have your gamma function values, and then you have your equations from the previous slide. You just plug it in, and you get your proper values. Now, if you want to look at the Weibull distribution itself of the problem, here it is. So here we have our median. This is zero point 0.5. Half of the successes here, half of the failures are here. Half of the successes are here on this other side. Now for the mean, there's a lot less success here to the right of the median, which is kind of okay, sure. And if you plug that into the reliability function, you will get a reliability of 0.422731. That's the median. Now, for the 10% of the dimensionless life, you get zero point 0.9 for reliability, and you will get this particular value of the rated life, which just so happens to be equal to 1. So again, standard deviation is this value, and then the RMS is this value. Um, that's basically it. There is a lot of maybe fresh concepts here. I'm not sure if Stat 101 discusses the Weibull distribution. I'm sure some electives discuss that particular statistical distribution. But aside from the difficulty with orienting yourself with the Weibull distribution, this is quite straightforward. Just understand what you're looking for and what functions or what properties should I use to solve for what's missing. And that is it. Oh, sorry about that. This has been 1 hour, right? Almost 1 hour. And I hope that you are well wherever you are and stay safe. Thank you so much.